So in this video, we are going to talk about how to analyze a situation involving an elastic collision in one dimension. We are going to imagine a situation in which maybe you have like a cart that has a known mass, and let's say just for now that it is going to the right initially. And so it has a mass of m1, let us say, and it has a velocity of v1 initial. And we have another cart, which can be going in the opposite direction. It actually doesn't really matter. It just has some velocity. They have to collide though, so in some way they have to be going in such a way that they will come together. And this cart has a mass of m2 and a velocity of v2 initial. And we are imagining that these carts are interacting on a track that has very little friction. And we are imagining that this is going to be an elastic collision. And so we're going to see what kind of conclusion we can draw from that situation here. The first thing, since there is no external force acting here, no net external force acting, at least in the horizontal direction, should mean either direction. Hopefully there's no friction and there's no, the normal force is equal to the force of gravity acting on each cart. So we can say that the total momentum at the beginning is going to equal the total momentum at the end. So we'll say that P1 initial, that's the momentum of cart number 1 initially, plus P2 initial, that's the momentum of cart number 2 initially, is equal to P1 final, that's the momentum of cart 1 at the end of the collision, after the collision, plus P2 final. And notice that these are being written at little lines across the top to indicate that they are vectors. We are talking about vectors here, so the direction of these velocities will matter. Because it's one-dimensional, we can take care of the direction just by writing plus or minus in front of the speed, and that gives us our velocity. We also have another condition, though. I said this was an elastic collision, and if it is an elastic collision, then the kinetic energy should be restored. So the total kinetic energy before the collision, which is going to be the sum of 1/2 m1 v1 initial squared, plus 1/2 m2 v2 initial squared, is going to equal 1/2 times m1, I'm going to down here write this down a little bit lower, 1/2 m1 v1 final squared, plus 1/2 times m2 times v2 final squared. So this just says that the total kinetic energy at the beginning equals the total kinetic energy at the end. Now to make this a little bit simpler to write, I'm going to multiply both sides of the right-hand equation by 2. That'll get rid of all the factors of 1/2. And so we can write our equation then a little bit simpler. We can just say it's equal to m1 v1 initial squared plus m2 v2 initial squared equals m1 v1 final squared plus m2 v2 final squared. And I make sure that gets on the recording here, what we just said. We haven't really changed the equation at all, we just simplified it a little bit. And it allows us to see more easily what we're doing with our little algebraic trick we're going to use in just a moment. So we're just saying that the kinetic energies are equal at the beginning and the end, because they said it was an elastic collision. We should also write the momenta on the left-hand equation in terms of their mass times velocity. So we have m1 times v1 initial. And remember, v1 initial can be either positive or negative. That's the momentum then. Plus m2 times v2 initial. equals, well, the momentum must not change because there's no outside forces taking momentum away from our system or adding to it. So it must be M1 times V1 final plus M2 times V2 final. Now, here is the little trick we're going to do, if you will. What we're going to do is we're going to take all of the terms that involve M1 and move them over to the left side of each equation, and all the terms that involve M2 and move those over to the right side of each equation. And this is going to allow us to greatly simplify our equation here. So I'm going to say M1 times the quantity. Well, we have V1 initial on the left-hand side of the equation. And on the right-hand side, we have M1 times V1 final. So we can just bring that over to the left side of the equation and make it a minus M1 V1 final. And then we can factor out M1. I've skipped a step there by doing the factoring after I brought the term over to the left-hand side. So you can see that becomes M1 times V1 initial minus V1 final. And then on the right-hand side, we still have M2. We'll do the same kind of trick. We'll bring over the other term involving M2, and we will write that as V2 final minus V2 initial. And then we have completed that process for that equation. And we'll do the same thing for this other equation over here. We're going to bring all the terms involving M1 over to one side of the equation, and the terms that involve M2 over to the right-hand side of the equation. So same idea, M1 times quantity V1 initial squared minus V2 initial squared, V1 final squared, I should say, is equal to M2 times V2 final squared minus V2 initial squared. And so now we're going to take advantage of the fact that on the right-hand equation we have each side has a difference of two squares, and there's a well-known formula for the difference of two squares. It's the difference between the two terms. That each of the terms you're squaring, you just take the term by itself, and it's the difference of the two terms times their sum. And so we're going to write this using that algebraic identity. What I'm going to do then is I'm actually going to divide that equation on the right by the equation on the left, which we can do because whenever you have equal things, you need to divide it by equal things, you end up with equal things. And so we're going to write the equation on the right in terms of that, using that algebraic formula I just mentioned. And then we're going to divide both sides of that equation by both sides of the other equation, which is a legal thing you can do. You still end up with an equation, still end up with an equality. So I'm going to write M1 times V1 initial minus V1 final times V1 initial plus V1 final. That's using that difference of two squares formula. And on the right-hand side, I'm going to say equals. On the right-hand side, it becomes M2 times the same idea. It's going to be V2 final minus V2 initial times V2 final plus V2 initial. And there we go. Now, as I said, we're going to divide each side of the equation by the appropriate side of the other equation, which you can do that as long as you're dividing by equal things. You can divide both sides of the equation by equal things, and we do have equal things in the other equation. So I'm going to divide the left-hand side of the equation by this term over here, and that will become then, in denominator, we now have m1 times v1 initial minus v1 final. And then on the right-hand side of that equation, we're going to do the exact opposite. We're going to divide by the right-hand side of the other equation, which is m2 times v2 final minus v2 initial. Now, look what this allows us to do. We have common terms in the numerator and denominator of both sides, so we can divide out those terms. So I'm going to divide out the m1 because there's numerator and denominator. I'm also going to divide out the v1 initial minus v1 final because that is in both the numerator and the denominator. And I'm left with v1 initial plus v1 final. And on the right-hand side, I do the same process. I divide out the masses, and I divide out the differences there, v2 final minus v2 initial. And I'm left with v2 final plus v2 initial. And so that leaves me with a very simple formula. I have v1 initial plus v1 final is equal to v2 final plus v2 initial. And now, to make this equation into something that makes a little bit more sense for us to understand what it means, let's get all the terms that involve the initial motion on the left-hand side, as we typically do, and get all the terms that involve the final motion on the right-hand side again. So I'm going to subtract v2 initial from both sides, and that's going to leave me with v1 initial minus v2 initial. And I'm going to subtract v1 final from both sides. That's going to leave me with v2 final minus v1 final. Now, this might be a little bit obscure what this represents, but let's just imagine that we have the situation where like we said initially, we have cart 1 going to the right initially and cart 2 going to the left. Well, that means cart 2 has a negative velocity. So what does v1 initial minus v2 initial mean? Well, if v2 initial is a negative number, what you're essentially doing is you're adding v1 initial speed and v2 initial speed. So adding the two speeds is basically how fast they're coming together. If one of them is going to the right at 20 miles an hour and the other one's going to the left at 30 miles an hour, then they're coming together at 50 miles an hour. Similarly, if on the right-hand side, this is at the final thing, well, usually what happens is, very often what happens in an elastic collision, you're going to have v1 cart number 1 going to the left at the end of it and cart number 2 going to the right. So let's imagine that's the situation here. What does that mean on the right? Well, it's kind of the same thing. Now you got v2 final going to the right and v1 final going to the left, but it's negative. So again, you're adding up the two velocities. What you're basically saying is this is how fast you're going apart, because now we've got v2 final going to the right and v1 final going to the left. And that essentially means that you're adding their two speeds to say how fast they are separating. So a way of expressing this relationship that we just derived is to say this is the speed of approach equals the speed of recession, how fast they're going apart. And it works, by the way, even if both carts are going to the right. Let us say that V2 or cart number 1 and cart number 2 are both going to the right initially, but they're going at a cart number 2 is going at a slower speed than cart number 1, so that they do approach each other and they have to collide. Well, that just means that the speed of approach, if cart number 2 was at rest, the speed of approach would be cart number 1's velocity. But because cart number 2 is not at rest, it's getting ahead a little bit, so the speed of approach is not quite as big as it would be if it was just the cart number 1's speed. And that's what we have over here. We're taking cart number 1's speed and subtracting from it cart number 2's speed to get the speed of approach. And what happens at the end? Well, now cart 2 is going to be going faster, because even if they're still both going in the same direction, Cart number 2 is going to be going faster because cart number 1 can't jump over cart number 2. And so now we say cart number 2 is going faster forward, but the speed they're going apart is a little bit less than cart number 2's speed. If cart number 1 has some speed, then we got to subtract that from cart number 2's speed to get the speed at which they're separating from each other. And so this really does show that the speed of approach equals the speed of recession in a one-dimensional elastic collision. Please note that it did not depend on the masses of the carts being the same. Sometimes in these formulas with momentum, we have to assume that, but not here. They can be different masses. The key thing was that momentum was conserved, as it always is, but it says an outside force, that means it's constant. And that kinetic energy was restored because this was an elastic collision and there's only motion in one dimension.